In the previous section, we looked at basic definitions that relate to graph theory in general, including paths and circuits. Now we're going to look at some actual applications and more details into graph theory. And we're going to look at specific problems like the Königsberg Bridge problem and other real-world problems. But when we first start looking at this, the thing that we need to focus on are Euler paths and Euler circuits. Now, this is named after a mathematician. It looks like the word Euler, but it's actually pronounced like Euler. So it's an Euler path and an Euler circuit. That might save you a little bit of embarrassment in the future if you're ever in a math class and they ask you to do something involving Euler, like Euler characteristics. You won't say Euler and you'll look super smart. My undergrad research was in Euler-Satake characteristics of orbifolds. So that's a mouthful in and of itself, but pronouncing that correctly, let's get that taken care of. Now we're going to look at some definitions of what an Euler path and an Euler circuit are. So looking at those definitions, an Euler path is a path that passes through each edge of a graph exactly once. So it goes through all of the edges on the graph, but it goes through each one of them exactly one time. An Euler circuit is a circuit that passes through each edge of a graph exactly once. So it's essentially the same thing as an Euler path, except it starts and ends at the same vertex. Path does not have to start and end at the same vertex. But an Euler circuit must start and end at the same vertex and go through every single edge of the graph exactly once. We can look at this in this example of city planning. A city crew must paint the median divider along each of the streets in the neighborhood shown below, starting and ending at A. The foreman wants to organize the route in the most efficient way possible, meaning you don't want to go over the same area twice. So can we do that? Can we draw a map to model this scenario? Each intersection is a vertex, each street is an edge. The definition of most efficient would mean that you don't cross over the same street twice. Thinking about how to do this is actually quite difficult. So starting from A, I could move either in this direction or in this direction. And then from either one of those points, I could go from here to here. But if I follow the same path and don't pick up my pen, we run into a slight problem. Because if I do what I just did and then continue on to over here, well, I'm going to have to go backtrack somewhere to get this spot right there. So thinking about this is actually a lot more difficult than you would think. Now, the basic graph of this would just be the connecting of each of these intersections, correct? But if you have to think about it, if you were to follow these lines in order to go from one place to another without backtracking might be impossible. So if you're trying to do this as most efficiently as possible, let's follow that red route using, let's do purple. If I were to start at A and move down and then move right, let's say I move down and down again, and then to the left to cover that street right here. Well, to get back, I have to cover that one again. So this one had two crossovers. And then go this way, and then get to here. But in order to get this street, if I go this street, I'm either going to have to go over it again and then move up, or I could go over and then go up the other side again. So if you think about it, you're going to end up with these crossing over the same street twice scenarios possibly. So if I were a city planner, I would want to make sure that I minimize the number of times that a crew had to go over the same street. So that would save time, it would save resources, etc. We're going to skip to example 3, which considers Euler's 7 bridges of Königsberg problem. This is a famous graph theory problem where Euler lived in this town, and the town had these bridges that crossed over a river. So this right here represents the river. And each of these little marks right here represents a bridge over the river. And you could get from each piece of land, the land is A, B, C, D. That's how they label it here. And so there are two bridges that go from A to C. There are two bridges that go from A to B. There's one bridge that goes from A to D. There's a bridge that goes from C to D, that's right here. And there's a bridge that goes from B to D right there. So we can actually take that like geographic map and turn it into a graph where each landmass is a vertex and each bridge is an edge. And this mathematician, Euler, was sitting there thinking, is there a way to start from A and get back to the same spot by crossing each bridge exactly once? So if I started here, and let's make my path in purple. And remember, if we want to start and stop at the same spot, but cross over each bridge exactly once. Let's think about some possibilities. I could go over from A into C, from C into A, from A into D, and D into C, but now I'm stuck. I can't get back to A without crossing a bridge I've already crossed. Let's try something else. What if I go from A to D and D into B, and then from B into A, and let's do C into A into C, and then C into A, and then I go from A into B, but I'm stuck again because I've used all three of these bridges. So this is what he was sitting there contemplating. And what he came up with is what we call Euler's theorem. So after studying this problem, thinking about it, experimenting with it, seeing what he could do, thinking about all the different possibilities, he wanted to figure out if this is even possible, okay? And he then figured out and determined mathematically what must always be true in certain situations, and that is what we will see as Euler's theorem. Before we address that, though, I want to make sure that we go over a couple of true or false situations, make sure we truly understand what an Euler path and an Euler circuit is. Remember, an Euler path is a path that travels through every edge of a graph once and only once. And an Euler circuit is a circuit that travels through every edge of a graph once and only once. So based on that, true or false, a path that goes through 5 out of 6 edges of a graph is an Euler path. Well, it has to go through every edge in order to be an Euler path. If it only goes through 5 out of the 6, it did not go through every edge, and so therefore that is false. B, a path that goes through 5 out of 6 edges of a graph exactly once and through the 6th edge twice is an Euler path. Well, it says that it goes through 5 out of 6 edges exactly once, but then it goes through the 6th edge twice. That would not be an Euler path because you can only go through each edge once and only once. So the fact that it went through that last edge twice, that is what makes it not an Euler path. And then lastly, a path that goes through all the edges at least once is an Euler path. Well, that's just based on the definition. That is true. All right. So let's take a look at an example before we hop into the Euler's theorem. So we're going to determine whether each given sequence is a path, circuit, Euler path, or Euler circuit. So a sequence is given to us and it goes through the vertices that we start with, and then we follow the path that it states through the entire sequence. So the first one I'm going to do in blue. We have starting at D, going from D to E, E to G, G to F, F to A to B, B to C. Okay, that is a path. Based on our definition from 13.1, if you want to review that, you would see that that is a path. It goes through in a sequence of adjacent vertices and the edges connecting them. It is not a circuit because it did not start and end at the same vertex. It is not an Euler path because it does not go through each edge of the entire graph exactly once. And so therefore, if it's not an Euler path, it therefore cannot be an Euler circuit either. All right, let's look at the next one. Let me erase the graph. Let's do this next one in purple. We're starting from F, F to G, G to E, E to D, then to G, then to B, then to C, then to D, then to B, then to A, then to F. Okay, so it is a path. It went through adjacent vertices that are connected with the edges, so that is a path. It's a circuit because it ended and started at the same vertex, F. It went through each of the edges exactly once. We had no overlap where we went over the same edge twice, so therefore it's an Euler path. And because it started and ended at the same vertex and goes through each of the edges exactly once, it is an Euler circuit. So that is an example of an Euler path and an Euler circuit. Now let's check out this last one. We'll do it in red. We start at C. It goes C, D, E, G, F, A, B, C. It's a path. They were all connected in adjacent vertices, connected by edges. It is a circuit because it started and ended at the same vertex. It is not an Euler path because there were 3 edges that we did not go through, so therefore it is not an Euler path, and it is also not an Euler circuit because it did not go through each edge exactly once. So hopefully that helps you to determine when something is an Euler path, when something is an Euler circuit, when something's just a regular path, when something's just a regular circuit. So let's get down to what Euler's theorem states. The following statements are true for connected graphs. Now, if you see there was an example of 7. It was missing the graph, so I just am going to go ahead and give this to y'all. These statements are true for connected graphs. So Euler's theorem works for graphs that are connected. Now remember that a connected graph is a graph for any 2 vertices in the graph, there is a path that will connect them. Euler's theorem states that if a graph has exactly 2 odd vertices, then it has at least one Euler path, but no Euler circuit. So remember that an odd vertice, an odd vertex, is a vertex that has an odd number of edges coming off of it. So if it has 2 odd vertices, and that's exactly 2 odd vertices, then it has at least one Euler path, but no Euler circuit. So that means that you can cross over each edge exactly once, but you will not be able to start and end at the same vertex while crossing over each edge exactly once. Each path begins and ends at one of those odd vertices. The second part of Euler's theorem states that if a graph has exactly no odd vertices, which means it would only have even vertices, then it has at least one Euler circuit. An Euler circuit can begin at any vertex. Okay, and then third, we have if a graph has more than 2 odd vertices, it has no Euler paths and no Euler circuits. So we're going to use Euler's theorem to determine whether there's an Euler path and or an Euler circuit. Put a check mark in the box if it has one of those or if it does satisfy that. So note that if a graph has an Euler circuit, can I say that it does not have an Euler path? No, that's not possible because a circuit is a path. Okay, so just keep that in mind. All right, so connected graphs, which have an Euler path, are going to have either no odd vertices based on the second part of Euler's theorem, because if it has at least one Euler circuit, that means it also has at least one Euler path. And then it will also be true that it could happen if there's exactly two odd vertices. An Euler circuit only occurs if the graph has only even vertices. Okay, so we're going to use Euler's theorem to determine whether the graph has an Euler path, but not an Euler circuit, or neither. So the graph has 102 even vertices and no odd vertices. So that is an example of using the second part of Euler's theorem, which means it would have an Euler circuit. So that is C. 10. The graph has 53 even vertices and 2 odd vertices. So that means that's based on part 1. It would have at least one Euler path, but no Euler circuit. So that would be B. 11. The graph has 45 even vertices and 3 odd vertices. Based on the third part of Euler's theorem, it would have neither an Euler path nor would it have an Euler circuit. And then lastly, we have a graph with 11 vertices, has an Euler path, but no Euler circuit. How many odd vertices does it have? It would have to have exactly 2 odd vertices. Okay, how many even vertices would it have? That would mean that it would have 9 vertices. 9 even vertices. Okay, that's based on the fact that it has an Euler path, but no Euler circuit. That is from that first part of Euler's theorem. So what that means is that we can stop using just trial and error and trying to go through a graph to see if it has an Euler path or an Euler circuit. What we can do is we can actually look at each of the graphs and figure out how many odd and how many even vertices they have. So for graph 1, I'm going to write at the top A, B, C, D, and E. And then we're going to write down in red the degree of each one. So A has degree 1, 2, 3, 4. B has degree 1, 2, 3, 4. C has degree 1, 2, 3. D has degree 1, 2, 3. And E has degree 1, 2. So graph 1 has exactly 2 odd vertices. Because of that, it would have at least one Euler path, but no Euler circuits. Do the same thing for graph 2. I'm going to list out all the vertices and then list out the degrees of each one. Go ahead and pause, try that one on your own as well, and then compare your answer. I can actually stop when I get to vertex E because I have 1, 2, 3 odd vertices already, and based on Euler's Euler's theorem, if there are more than 2 odd vertices, then there is no Euler path, which therefore means that there's no Euler circuit, and that's because there are 3 odd vertices, which is greater than 2. Okay, so then we do the same thing for the third one. In graph 3, they have all even vertices, which means that there is at least one Euler circuit. Okay, meaning that means that there's also at least one Euler path because an Euler circuit is an Euler path. Okay, so we can use the Euler theorem to determine whether or not we have any Euler paths or circuits based purely on the degree of each vertex and whether the vertices are even or odd. So mathematicians build off of other mathematicians' ideas, and there's a mathematician, Fleury, who came up with an algorithm for actually finding where the Euler path or Euler circuit is using a certain procedure. So essentially what he determined was, first you look at Euler's theorem and you determine whether or not the graph has an Euler path or Euler circuit. If one exists, then you continue on. And so if you have a graph that has exactly two odd vertices, it contains an Euler path. So let's label that. It contains an Euler path. And so you just need to start at an odd vertex. If there are no odd vertices, then it contains an Euler circuit. UIT. You can start at any vertex. So then you're going to number the edges as you trace through the graph according to the following rules. Since you can't trace edges twice in an Euler path or circuit, consider edges already traced as invisible. If you have a choice of edges, choose an edge that is not a bridge. Remember, a bridge is an edge that if you removed it, it would create a disconnected graph. So you want to avoid that and only choose a bridge if there's no other option. And then continue with each edge until every edge of the entire graph has been used. Okay. If a graph has no odd vertices, where should you start? No odd vertices, we're going to start anywhere. If it has exactly two odd vertices, you need to start at an odd one. And if a graph has more than two odd vertices, where should you start? Don't start at all, because there is no Euler path and Euler circuit, so therefore you'd be wasting your time. Okay, so using that, we can answer these two questions. True or false? When using Fleury's algorithm to find an Euler circuit, always begin with an even vertex. That is false. Okay. The basic rule in Fleury's algorithm is A, never travel across a bridge of the untraveled part of the graph, or only travel across a bridge of an untraveled part of the graph if there is no alternative. That's going to be B. You want to avoid it as much as you can. Okay. There are some great examples in the book of using Fleury's algorithm to find circuits and Euler paths. We're going to do one together right now, though. First thing we're going to do is we're going to look at this graph below, and we're going to use Euler's theorem to determine if the graph has an Euler path or an Euler circuit. So that means we need to look at the degree of each of these vertices. So I'm just going to write the degree next to each vertex. So L has a degree of 2, J has a degree 1, 2, 3, 4, H is 2, D is 4, C is 2, B is 4, A is 2, G is 4. K is 4, 1, 2, 3, 4. I is 4, F is 1, 2, 3, 4, 4, and 4. So this has all even vertices. That means it does have an Euler circuit. So based on that information and Fleury's algorithm, it asks, can we start at any vertex or only a particular one? And so because we have all even and no odd vertices, we can start at any vertex. Okay, so we're going to choose a starting vertex. At which vertex should you end? So if I pick one and I'm going for an Euler circuit, I want to make sure that I'm in at the same vertex. So I'm actually going to let's start at L. Start at L, I want to also end at L. And I want to make sure that I go through every vertex exactly once. Or sorry, go through every edge exactly once. So I'm starting at L. I'm going to go down to G, go down to A, go over to B, go over to C, go up to D, go up to H, go up to J. So notice I've gone through every edge exactly once. Then I'm going to go to I, and then I'm going to go to D, F, B, E, G, K. I'm going to go down to E, F, I, K, J, back to L. That is one Euler circuit right there. I went through each edge exactly once. I know it looks like I repeated right here because I had a little hiccup with my pen, but I went through each one exactly once. Okay, so that's essentially the gist of what we're doing. We're determining how many Euler paths or circuits there are. We're using Fleury's algorithm. Hopefully this makes sense. If you have any questions, let me know. Thank you.